University, whose PhD investigates the molecular evolution of sea spray aerosol chemistry from laboratory systems to the eastern North Atlantic. Her research spans atmospheric composition, gas particle partitioning, heterogeneous and multi-phase chemistry, and cloud-mediated aerosol aging. She is skilled in advanced mass spectrometry and aerosol measurement techniques and has held in key leadership roles, including president of the NOSA Early Career Scientist Board. Sneha's work has earned multiple awards and she has published in leading journals. With this short introduction, on behalf of IITM and also the Early Career Researchers Hub at IITM, I would like to introduce, welcome you to give this talk. Thank you again. Thank you.
Thank you so much for the very kind introduction. Good afternoon to everybody, and thank you so much for inviting me to give a talk. Today, I will share how we used chemical ionization mass spectrometry, SIMS, to understand the chemical composition of sea spray aerosol at a molecular level, and also how we decoded mechanisms understanding gas particle partitioning at the aerosol particles. Bringing me to the title, that can sea spray aerosol be a source of gas phase PFAS? Molecular insights from high resolution mass spectrometry. So before diving in, let's begin with the basics.
I think you have to point it this way. Yeah.
Yes.
So let's start with understanding what are sea spray aerosol. So sea spray aerosol are formed when ocean waves break and they entrain air into the ocean, forming bubbles, which, by rising to the surface, scavenge surface active material and burst and release a complex mixture of inorganic sea salts and organic compounds, which we call sea spray aerosol. But why do we care about them? It's because they have both direct and indirect effects on radiative forcing. They can scatter the sunlight back to the atmosphere, back to the space, thereby cooling the planet. And they can also act as cloud condensation nuclei and ice nuclei, thereby affecting the cloud properties. Hence, they have a role in global Earth surface temperature. Next, they provide a surface for a lot of gas to particle and particle phase chemical reactions. So they modify the entire atmospheric oxidative balance and hence play a big role in atmospheric chemistry. And they also provide a medium or a vehicle for transport of nutrients, contaminants like microplastic, and even bacteria and viruses from the ocean to the air and vice versa. So it helps in cycling of various materials. Despite these the importance, there is some knowledge gap. We do not completely understand the chemical composition of sea spray aerosol, especially at the molecular level. And this has been mostly because of lack of real-time, selective, and sensitive measurements. And to tackle this, we employed chemical ionization mass spectrometer, which uses soft ionization technique. So basically, the sample air molecule reacts with the reagent ion molecule to form an adduct, which can be detected. For example, this is your sample air containing all the molecules. And how this instrument senses any molecule is change in voltage or change in electric current. So we need to charge the neutral sample air molecule with a plus or minus. So we have a sample air molecule that reacts with the reagent ion and forms a charged molecule. For example, here the sample air goes in, mixes with the reagent ion, in this case iodide, and forms an adduct. So iodide sticks with the molecule and attaches with the molecule and forms an adduct, which then travels to differentially pumped chambers and through the ion optics finally reaches the time of flight chamber, where it's segregated based upon the mass to charge ratio. And what we see at the detector is also the signal or the voltage gradient because of the charge. What we get in the end is mass spectrum. So on x-axis, we get m over z, basically the mass to charge ratio of the molecules. On y-axis, we get instrument response or signal. And then we usually subtract the background of the instrument from our sample observations and use various calibration methods like standard gas cylinders, permeation tubes, and liquid calibration system to convert the instrument response to concentrations. Next, since the title is Can Sea Spray Aerosol Be a Source of PFAS? So let's also understand what PFAS are. So PFAS refer to per and polyfluoroalkyl substances. Basically, these are persistent human-made organics in which a hydrogen of the carbon chain is either partly or fully replaced by fluorine atoms. And they have been widely used in food packaging, non-stick cookware, firefighting foam, waterproof clothing, and that's because of their unique physical-chemical properties. For example, the carbon-fluorine backbone is hydrophobic in nature, while the functional group attached at the end is often hydrophilic. For example, carboxylic acid, sulfonic acid group, or phosphate group, which makes this molecule amphiphilic. So both hydrophobic and hydrophilic at the same time, making it highly surface active and ideal for purposes like firefighting foams. The next unique property is the strong bond between carbon and fluorine. This is one of the most strong bonds in the chemistry, and therefore they are resistant to thermal, physical, and even biological degradation, making them earn their nickname of forever chemicals. So these chemicals, once released into the atmosphere, they can turn into the end products, which could be simpler PFAS compounds, but they can never be totally eradicated once they're released. And hence, it's a big problem now. And there have been several policies like Stockholm Convention in Europe that has banned several species of PFAS, and they can cause reproductive damages, cancer, can be found everywhere from breast milk to blood. But the combination of this strong carbon-fluorine bond and the hydrophilic nature also makes it highly soluble in water. And hence, oceans become a global reservoir of these PFAS, especially the ionizable species like one with the end group as carboxylic acid or sulfonic acid. And as a result, they have been found everywhere from surface waters to deep oceans to coastal waters. For example, here is a study by Muir and Mias, 2021. And the main message behind showing this plot is basically that perfluorocarboxylic acids, PFCAs, and perfluorosulfonic acids, PFSAs, have been found across global oceans, everywhere. The main message is that they are widespread and they're present everywhere in the oceans. To be specifically looking at one ocean, Atlantic Ocean, for example, because this is where our study was done. So there was a study by Savido et al. In 2023. They did this Atlantic meridional transect from 40° north to 40° south. And they collected seawater samples during October-November 2019. And they did solid phase extraction to get PFAS out of the samples, froze them, and then came back to the lab and used liquid chromatography for measuring the PFAS concentration. And what they found was here. So on the x-axis, we have the latitude from 40° south to 40° north. On the y-axis, we have depth. So they also measured at different depths from surface water to 5,000 meters deep. And the blue bar shows the concentration of PFAS. Towards red, meaning higher concentration. Two main messages from this plot is that if you look in the southern hemisphere versus northern hemisphere, we have more PFAS concentration in the northern hemisphere, which makes sense because we have more anthropogenic sources in the northern hemisphere than the southern hemisphere. The second key message from this slide is that there is more on the surface than at the depth. And that's because I told you that they're amphiphilic in nature. So the hydrophobic end wants to stay in the water, but the hydrophilic end wants to stay in the water, and the hydrophobic end keeps protruding out. So they accumulate at the surface. And this also happens to be the sampling location of our study, which is likely a PFAS hotspot. And I would also like to mention that there is a gyre in this area which concentrates all the plastic pollution, and it's also a garbage patch.
What is the other peak? The CTD 013.
Here.
Yes.
I think it's just maybe closer to the gyre because we were not in the gyre. I think this is probably in the gyre. Yeah. Now that we have understood what are sea spray aerosol, what are PFAS, let's see what is the link between the two. So as I told you, they are surface active. And therefore, there was a study by Casas et al. They calculated enrichment factors. So basically, you measure the concentration of PFAS in the surface microlayer and in the bulk water and take the ratio as an enrichment factor. And you can also do this for the sea spray aerosol. So here is the plot for enrichment factors in the sea surface microlayer. So on x-axis, we have different PFAS species. On y-axis, we have the enrichment factor in the surface microlayer. And you can see that PFAS are enriched by about 1.2 to 5 times in the microlayer than the bulk water, owing to their surface active nature. And if you look at the sea spray aerosol, this enrichment can go up to 5,000 times. So they are highly enriched in sea spray aerosol particles. And it's likely because the aerosol particles have a higher surface area to volume ratio, so there is more surface to get enriched. So this has been long established that sea spray aerosol act as a source of particle phase PFAS. In fact, there has been a range of concentration at 0.67 to 24 picogram per cubic meter on average is emitted as particle phase PFAS from sea spray aerosol, which acts as an important medium for its long-range transport, not only across remote regions, but also across hemispheres. But what about gas phase emissions? These studies have only focused that particle phase PFAS can be released, but can gas phase PFAS emissions be also there from sea spray aerosol? This is the question that we wanted to answer. For this, we went to a field campaign called Agena, aerosol growth in the Eastern North Atlantic. And this was in the summer of 2022. And it was on a small island called Graciosa, in the middle of nowhere. So we could be as remote as possible to just measure the marine sources. And this is a screenshot of the container with all the instruments. So we had a sea spray simulation chamber and the SIMS chemical ionization mass spectrometry. We also did some aging experiments using the PAM and measured particle number, concentration, and size distribution using TMPS or SMPS. I will only focus on tank and SIMS in this talk. And if you look more closely at the experimental setup, so each experiment started with me collecting the real ocean water and then adding it to a sea spray simulation tank. Basically, it has a plunging jet mechanism. So the water keeps recirculating and falls onto the surface of the water, mimicking wave breaking and entering airs to form bubbles, which release sea spray aerosol, a mixture of both particles and gases, into the airspace. And then this aerosol-laden air is sampled with a chemical ionization mass spectrometer using iodide as a reagent ion in this case. We also sampled ambient air so that we could later compare our tank simulations with the ambient observations. And just to be clearer with the terminology, all the results from the tank, labeled as ambient.
Do you always sample from the coast itself, or do you have some open ocean sampling also that coastal? And same coastal area or around the island?
Same area.
And bucket sampling?
Bucket sampling, I also took a bucket background. Bucket background. There were some emissions coming from that. And each experiment was completed on the same day. The water was collected. So now coming to results, I will first show you the overall gas phase chemical composition from the tank experiments. So here is a pie chart. So we see about 40% is from organofluorines, 40% from organics containing C, H, and O, and about 10% organonitrates, organosulfates, and a very small fraction of chlorine containing organics. And our next idea was to see if this matches with the ambient observations. So what we did is a wind sector analysis. So now I show you the map of the island where we were measuring, and the star marks the sampling location, the container where the experimental setup was housed. And on the left or the west of the sampling site, we had an airport. So when the wind came from north and northeast during midnight or early morning hours, we see that the composition matches quite closely, the overall composition. We have similar large chunks of purple and green and smaller of sulfate and nitrate containing compounds. But if we look at other wind directions, from east, west, or south, during daytime and polar chemistry is active, we see a different composition, usually an increased contribution from CHO compounds.
What's the lifetime of these species in the atmosphere?
For the gas phase PFAS, I couldn't find it, but I would assume low because they are mostly, so to be able to stay in the gas phase, they need highly acidic pH, and the environmental pH is not so acidic in general. So I would assume it's low, but I'm not aware of it.
But they are long-lived species, right? They're forever chemicals.
Yes, but if they would stay in the gas phase or would convert into particle phase, I said if they will not be destroyed, but they could partition.
So you mean uptake is lower?
I think so.
So why does photochemistry play a role then?
So this is overall composition and not molecular level composition. So it could be also that different compounds are coming, different molecules are coming into picture. So each pie here is size according to the total signal. And you can see that these pies are bigger. So I assume that there were just in general more sources. And at the molecular level, they could be still similar. For example, these two had even similar composition during at the molecular level. So they have similar PFAS species. But my intent to show this was how well is tank replicating the overall composition. But for PFAS species, we see it from all the directions. But photochemistry does have a role. There have been some studies showing that fluorotelomere alcohols, these FTOH species directly released from polymer factories, they could undergo photochemical oxidation to form perfluorocarboxylic acids, but not up to very high concentrations, usually in 1 ppm. So overall ambient gas phase composition looked similar when the nascent sea spray aerosol came from north and northeast, especially during the hours when photochemistry was switched off. And also during these periods, we had very high glyoxal peaks, which is well known to be formed from photochemical reaction of fatty acids released from the ocean. So what we can conclude from this is that tank can replicate gas phase composition of sea spray aerosol under remote marine conditions, at least at night, when the wind is coming from the clean marine sector. Now, we decided to compare this pie chart and these two, basically when the marine was similar, when the ambient was similar to the tank, and looking at the CHOF compounds specifically. So if we zoom in into these purple segments, we found that all these fluorinated compounds belong to the class of perfluoro and polyfluoroalkyl substances. Specifically, they are trifluoroacetic acid, perfluoropropanoic acid, perfluorobutanoic acid, and perfluoropentanoic acid. So they're all perfluorocarboxylic acids. And this was a surprising result. Let's also look at the molecular level composition. So here is a time series of the PFAS signal from experiments and the ambient air. So on x-axis, we have the sampling period. On y-axis, we have concentrations in ppt. The orange boxes represent signal from the tank experiments, and blue is the ambient observations. And what we see is that tank is always higher than the ambient concentrations, and they follow somewhat a similar trend, but not throughout the sampling period, likely indicating that sea spray aerosol is a source of gas phase PFAS in the ambient air, because in the tank we have no other sources but the seawater.
But your tank bubbling speed, do you regulate that according to the ambient wind speed?
No.
So I mean, those peaks that you're seeing in the ambient, have you tried correlating them with wind?
Yes, I did. So the wind speed was more or less around 5 to 5.2 meters per second during the sampling period.
See any?
Still not sure what those peaks are, but I've checked all the meteorological parameters. There is higher temperature in the end of the campaign, but it's not so high to cause such a big change. But it could also simply mean that there are other sources that come into play during the end of the sampling period, because we are saying that ocean is a source, but not the only source. There could be also direct emissions from the industries and other emission sources.
That's why the peaks are higher.
Sorry?
Other sources contributing also the peak of the tank.
For the tank, so we also thought that it could be the case, and therefore we did a lot of background measurements that I'm going to show in the next slide.
Some of the concentrations are also in negative variability. So is it detection limit?
So when we did these also.
Yeah.
So when we did these measurements, how we operated our SIMS was that the ambient air was sampled at the ambient humidity, but the instrument zeros were done using ultra high purity nitrogen, which is completely dry. And when I did convert them into concentration from signal, I had to do some RH, relative humidity dependent sensitivity calibrations. And we found that the signal is increases with humidity, so it becomes more sensitive. And then after correcting for it, this goes to 0. So I think it's below the quantification.
So just being a little pedantic, but that's not concentration, that's mixing ratio.
Yes, sorry, mixing ratio. The tank, so I was saying that we thought that this was a very surprising result, because no other study has so far reported gas phase PFAS emission from sea spray aerosol. And we were thinking if we are only measuring the background or if we are only measuring the tank itself. So we did a series of controlled laboratory experiments to establish the background. So we measured sodium chloride in milky water in the same tank at the same sampling conditions with the same instrument, same settings. Then we spiked the sodium chloride water with 1.72 nanogram per liter of pure PFAS standards. We increased the concentration 10 times and 100 times. And instead of sodium chloride, now we added the artificial sea salt mix. And for the spike levels, we don't see such a difference. And it's still lower than the average instrument background. So we don't think we are measuring the background from the tank setup itself, but from the tubing, there was some signal which has already been accounted for. And all the SIMS backgrounds have also been accounted for in the real seawater samples. So
is this the focus or which instrument is this?
iodine.
Iodine one.
These are all oxygenated carboxylic acid species.
But the iodine one or the ionocon one?
Iodine. So there is no gas-based PFAS from artificial seawater samples, despite spiking 100 times. Even with 172 nanograms per liter, there is no difference between no spike and 172 nanograms per liter. So we think that artificial seawater does not release gas-based PFAS, and it could be either due to lack of organics, or it could be that the organics somehow affect the properties of the aerosol particles, which is then responsible for partitioning of PFAS. And another sanity check was to also measure water samples from around Sweden and see if we can see gas-based PFAS.
How do you calibrate the SIMS for PFAS?
So we used two different methods. We first used liquid calibration system, and then we have, for example, trifluoroacetic standard. We added to the liquid calibration system where it evaporates it and mixes with nitrogen and then pumps it into the instrument. And the second method, we also found in another paper from me that the collision limited sensitivity or the maximum sensitivity the AIM SIMS can have is same between different reagent ions. So if you have the same reactor geometry, same voltage settings, and basically that's it. Same reactor geometry ensures same reaction time, same flows. Then you can, under the same settings, get the same maximum sensitivity across benzene, iodide, bromide, different reagent ions. So the second method for quantification was that I determined the maximum sensitivity of the instrument using benzene mode. They overlap. So I got from iodide about 13 normalized counts per second per ppt for TFA, and also the similar collision limited sensitivity.
But there's no direct standard available for.
There is. I used a direct TFA standard. We observed.
Okay.
We used TFA, PFBA, and PFPEA. We only did not get standard for PFPRA. So I took the average. They're all about the same. Yeah. So now I was saying that for another sanity check, once we made sure that it's not the background, we wanted to see that if we can also replicate from other water samples. Since it was practical to go back to Azores, we collected water samples from east and west coast of Sweden. And you can see that here, 4 panels show different PFCAs, CFA, PFCRA, PFBA, and PFPEA. Basically C2, C3, C4, and C5. And we see that all real seawater samples tested positive for gas-phase PFAS signal, which means that they all release, but the magnitude is quite different. And this could be perhaps because of difference in salinity, difference in organics, maybe difference in just starting PFAS concentration in the water. We don't know yet. So once we now know that our signal is real, it's still surprising. What could be the mechanism behind gas-phase PFAS signal from sea spray aerosol, especially given their high solubility in water and very low pKa values? So when something has very low pKa, it will stay in the condensed phase unless the pH is lower. For example, if pKa is 2 and aerosol pH is 3, then it will stay in the condensed phase. It will only get to gas phase when the pH is lower than 2. So to figure this out, we did another set of controlled laboratory experiments. So there was an additional setup. So all this is same, but we also used a 200 ml laboratory bottle because we also wanted to change the pH of water samples. And as you know, seawater is a natural buffer, so it's very difficult to change pH of large volumes of water. So we took smaller volumes. And here are the results. So here on x-axis, we have salinity. On y-axis, we have total PFCA mixing ratio. And the color bar shows 1/over pH or acidity. So more red is more acidic. And different shaped markers show different kinds of water samples. So if we first focus on this rhombus here, so it's low salinity artificial seawater, and it does not show any PFAS signal in the gas phase. Now, even if I spike it, the yellow golden dot is basically symbolic of spikes. So even if I add PFAS standard to it, no signal. Even after acidification, no signal. So low pH and low salinity artificial seawater cannot release gas phase PFAS. But if I now take higher salinity artificial seawater, representative more of global oceans, still no signal. After spiking, no signal. But if I acidify the same water sample, we do see PFAS in the gas phase. This indicates that high salinity artificial seawater does release PFAS in the gas phase if the pH is low. Then we were motivated to test real seawater samples. So here we have Baltic seawater at its original salinity of about 5 to 7. We don't see any PFAS. Then I thought perhaps just increasing the salinity would be enough. And I increased the salinity, but it actually decreased the signal slightly. And my hypothesis is that in a low salinity solution, it's basically salting in effect. So it's providing more water of hydration around PFAS molecules, making it more soluble and further suppressing its partitioning to gas phase. But when we add acid to the same increased salinity Baltic seawater, there is gas phase PFAS signal. Please note that the Baltic seawater samples were not spiked with PFAS. So acidifying Baltic seawater does result in gas phase PFAS signal, indicating that low pH or acidic particle along with high salinity have a role to play in gas phase PFAS signal.
So what acid you use for acidification?
I used 2 normal sulfuric acid.
Is it not like because it's a carboxylic acid? So if you're keeping one environment as like sulfuric acid rich environment, so it will partition into like water phase, and it will make COO minus as COH, right? That is making more like basically because it will come in a molecular phase than a ionized phase.
Exactly. Yeah, we think exactly that is what's happening.
So if you have like if you make it in a like CO2 rich or carbonate rich environment, attaining the same pH with that similar kind of like
Carbonic acid, it's difficult to reach at low pH. So there have been some studies showing that sea spray aerosol does have a very acidic pH, especially the submicron particles. I think this was a PNAS by San Diego group. And they basically used a low LPI, this low pressure impactor, and loaded filter paper, litmus paper on different stages and collected aerosol particles. And they found that the lower stages were acidic below pH 2. So that's why I used sulfuric acid to simulate a similar pH value.
That's for aged aerosols, right? Here you're getting like fresh ones in your tank.
Yes, but once they're released from the tank, I was also mixing it with some dry zero air because I was also doing aged experiments, so to maintain similar humidity for both the experiments. But that's in the next slide. What could be driving this aerosol pH, even if we are not aging it in the chamber? So what we think is that it's the relative humidity. So on x-axis here, we can have salinity. Y-axis, we have PFAS mixing ratio, and this is colored by relative humidity. And triangles are Baltic seawater, and circles are hot seawater. So it is most important. So you see that when I mix dry air into the Baltic sea spray aerosol sample, the PFAS signal increases by about 18%. And if I do same with Gothenburg water or North Sea water sample, the signal increases by about 65%. And if I increase the salinity of the same water, the signal drops, again salting in effect at low salinity. But now, if I mix dry air, the signal increases 86% from the original Baltic sea water sample. So I think what's happening here is that drying within the lines till the time it reaches the mass spec is already starting some level of aging in the aerosol particles. But no photochemistry, no chemical reactions, just drying is enough to switch on this acidic nature of the particles.
But finally, you're measuring it in the gas phase, right?
Yes.
So then if you're saying drying is such an important factor, then your wall effects will be pretty large, even in your inlet line, right? Because as your aerosols are traveling through, they are depositing on the wall and they are getting drier and drier. So
What we have used here is mostly Teflon tubing, all Teflon tubing, which should be less sticky. And we had a very high flow rate, very low residence.
the sea salt, yeah, it will.
Mhm. Even there, that's unavoidable. But we tried to keep a laminar flow, high flow rates in the tubing.
Did you do some time series observations for these to see if it changes over time? Is there an increase or decrease with time with the same tank setup?
So on the same day,
Yeah.
I think it more or less stays the same. For the ambient, we had the inlet flow rate of about 12.7 liters per minute. I don't think that maybe wall losses were not so
Not
big.
losses, sources.
Sources.
You're saying as it dries, it leads to more emissions, right? It would become a source.
Do you think there will be salt stuck on the tubings and then it will?
Yeah. So like when you make observations in coastal regions or even on ships, etc., eventually all tubes you get them coated with sea salt, where you have to change them fairly regularly, right? So if that's happening continuously, then that would be a positive bias to your.
See an increase and decrease during the measurements I did short time series. But it was like this and then
It was over days, right?
yes, that was over days. But we were using the same tubing.
Yeah.
So if it were only coming from the particles accumulated on the walls, it should have always gone up. But it varied even in the tank.
No, but you were not continuously running the instrument.
Continuously running the instrument.
So when you change the water in the tank, the instruments.
Ambient.
Okay.
All the time measuring the flow.
Right. Okay.
So what this plot tells us that drying the particle enhances the partitioning of PFAS into the gas phase. And we hypothesize that it's likely concentrating the organics and salts into the particles, leading to a decrease in pH, which then facilitates the partitioning to gas phase. And we also have proposed a mechanism behind this. So the freshly released sea spray aerosol particle is crystalline in nature. So sea spray aerosol is not only sodium chloride, but a mix of other magnesium salts, potassium salts, and even organics. So when it's freshly released, several studies have shown that it's crystalline with a core of sodium chloride and a diffuse layer of organics with potassium, magnesium, and calcium. But as it is released into the atmosphere, it dries, which changes the morphology to core shell. This has also been published in some microscopy studies. So what happens is that sodium chloride from the core moves to the periphery of the particle. And with the external coating of compact organics, what happens is that it dries, the pH decreases, the organics do not have any ions to chelate with. So they neutralize and go to the periphery. And magnesium and calcium no longer have bonds to form with organics, so they move to the periphery. And somehow sodium is here, and we hypothesize that it could be due to its bond-forming ability with the organics. And also, second hypothesis is that 4-fluorocarboxylic acids are likely present as salts of sodium. So when this morphology shift is happening, that sodium chloride is moving from the core to the surface of the particle, it's also pulling the perfluorocarboxylic acids towards the surface of the particle. And then this meets with a simultaneous decrease in pH because of concentration of salts and acids, which intonates them. So the ion combines with H+ to form the neutral species, which then volatilizes and partitions into the gas phase, and we are measuring it. So two main points: that morphology changes lowering the pH, and PFCAs are likely present as sodium salts, which protonates on the low pH to release PFAS in the gas phase. We also made a model based on the proposed mechanism. So here, on x-axis, we have DMSO, dimethyl sulfoxide, a signature marine compound from DMS oxidation. On y-axis, we again have the PFAS compounds, and they are colored by nitric acid signal. And you can see
The DMSO is also from your SIMS itself, similar to the same scans.
yeah, the same scans, exactly same. So you can see that they follow almost a linear curve with about 60% variation for all PFAS compounds being explained by this model. And we see higher signal when low FOIL, which means higher nitric acid, which also supports that low pH is needed. And such high explanation of the marine species also points towards sea spray as a source. So it supports our hypothesis. And we also compared previous gas phase measurements. I said that there are no gas phase PFAS reported from sea spray, but there have been some gas phase measurements, not from sea spray. So there was this study by Young et al. In Toronto, and they measured in the year 2022 on the university building. So it's an urban setup. And they plot the diagonal cycle here. So on y-axis, we have TFA, the trifluoroacetic acid in black, with ozone flux, ozone temperature, and formic acid. And they have a concentration ranging up to 1, a mixing ratio up to 1 ppt. Now, if you look at our observations, so say on x-axis we have hour of the day, and here we have TFA, PFPRA. The TFA is in black, and they reach up to 100 ppts. So that's 2 orders of magnitude higher than what has been previously reported. But for a sanity check, I also plotted formic acid here. So the formic acid, we had up to 2 ppb, and they had up to 1 ppb. So it falls in the same order of magnitude, pointing towards not any error in the instrument. So we conclude that there is likely an underestimation of gas phase PFAS sources, especially in the marine regions. And this could affect the budget of atmospheric gas phase PFAS as well as their long range transport to remote regions. This brings me into the conclusions. So we noticed ultra short chain perfluorocarboxylic acids, both in ambient air samples and tank experiments from Azores, indicating that sea spray aerosol is a source of gas phase PFAS in the ambient air. And we hypothesize that it's the low pH of the sea spray aerosol that drives the partitioning of PFAS into the gas phase. And our measurements reveal significantly higher concentrations of perfluorocarboxylic acids than previously reported in the literature, pointing towards a previously unrecognized large source of gas phase PFAS, with implications not only on the budget but also long-range transport pathways. Our findings also introduce a new understanding of gas to particle phase partitioning of these species and highlights the importance of acidic pH of sea spray aerosol. I think it's not only gas PFAS which is partitioning into gas phase, there could be other low pK molecules that are partitioned into gas phase from the surface of sea spray aerosol. Next, I thought to include a slide, how is this all relevant for India? So PFAS are persistent, mobile, and as I showed, they are globally present. So the same ocean-atmosphere exchange mechanism over Atlantic should also be applicable over Arabian Sea and Bay of Bengal. And it could be especially interesting to link it with monsoon winds in the extensive coastal regions and see how these wind patterns change the concentration and interaction of these gas-phase PFAS. And if we talk about the SIMS, I think that also has a high potential to measure a mix of complex reactions in the Indian atmosphere, where we have very high interactions between anthropogenic and biogenic emissions, big range of relative humidity. So there is a good scope using different reagent ions. We can get SOA precursors to SOA molecular composition. With that, I would like to thank you for listening and welcome any questions.
Sneha, we'll open the floor for discussion, please.
It was a very nice talk. So my question is after hearing you and about all these things, so I am guessing, so if you have phytoplankton plume or high DMS emissions over the ocean for a particular time of the year, immediately after that you should see a higher concentration of PFAS, these compounds in the atmosphere, because DMS will lead to sulfate production or sulfuric acid production in the ocean atmosphere. So will it lead to the higher exchange of these PFAS compounds from ocean to atmosphere?
Thanks for the question. I think what is driving the pH of sea spray aerosol is concentrating of concentration of acids and salts, and not TMSO or sulfur oxidation products. That's what I think. And also, my motive behind showing the model was that it relates well with TMSO, but doesn't mean that TMSO is somehow participating in PFAS release. It was just trying to show that they're likely coming from the same source. So I don't think that if there are higher levels of TMSO during phytoplankton blooms, there will be also higher PFAS. But if there are higher DMSO levels because of monsoon winds and they're being transported more to the inland, that's a different story. Then also mean that there was larger sea spray aerosol emissions reaching the mainland. In that case, I think there would be also higher PFAS emissions.
So, like this PFAS will anyway be in the core shell of your like emitted sea spray aerosols, right? Suppose if phytoplankton emissions are they are emitting DMS, okay, and these things are getting converted into H2SO4, okay, through photochemical aging and oxidations. So because there is no emissions of ammonia to neutralize that. So, or any other compounds to neutralize those sulfuric acids that are being produced over the oceanic region in a remote conditions. So whether because PFAS will already be there within that core shell of your emitted sea sprays, right? So whether the change in gaseous concentration of sulfuric acid will cause the emissions of, will trigger the emissions of these PFAS or not. Okay. My question is in that.
Yeah. So you first said that there are not so many neutral species, but we measured a lot of gas phase urea and dihydroxyurea coming in gas phase from sea spray aerosol.
That will be mostly, right?
We measured in these ambient observations over the Atlantic. So I think there are also biogenic sources. There was a paper recently where they did an aircraft campaign over the Atlantic Ocean, and they also measured high levels of gas phase urea from sea spray aerosol. So it does come from marine source. Coming to your sulfuric acid concentration triggering protonation of PFAS, I'm not sure, but I think that as soon as sulfuric acid is formed, it will leave the particle. And then what is controlling the pH of the particle is perhaps not the DMS oxidation products, but already the acids, the organic acids and salts that are present in the sea spray aerosol. Why I'm saying is this, we have done some pH measurements again in the lab using not so productive seawater samples, and we still see very low pH for the sea spray aerosol particles. And what is triggering here the gas phase PFAS signal is low pH. So even the Baltic Sea water in the tank did release PFAS, but not as much as the Atlantic Ocean water, which means that low pH is the triggering. If I'm able to put across my point.
I think he's asking about that relationship between your DMSO and right, and I think it's very clear that your DMSO increased concentration does show there's higher acidity. I mean, it will contribute. So sulfuric acid doesn't leave the particle; it actually goes into the particle. So it's going to have some
in ocean atmosphere now. So you'll always have liquid water into your aerosol phase. Right? May not be in daytime, but maybe in nighttime because of the temperature.
Daytime also it's acidic, right? But yeah, it's a combination. Obviously, sulfur plays a role, but your organics are also playing. But I'm pretty surprised to see that positive correlation all the time because your DMS is all biological activity. But what are you saying is biological activity is not the only thing controlling it, but it's actually oxidation that's controlling it, the relationship to PFAS, right?
No, I was saying that it's likely just the same source, that when we had more DMSO in the ambient air samples, meant that more of it was coming from the ocean.
No, that's not always the case because it depends on your biological activity. So if you don't have any phytoplankton activity, even if you have high wind, you won't get any DMSO.
Yeah, stable chlorophyll was quite low when we were measuring there.
Yeah. No, but the fact that you have DMSO shows that there's a lot of biological activity. I mean, increasing DMSO is very clearly phytoplankton related. It's not just a SE exchange issue, right? You need to have it in the seawater.
There is definitely some DMS which is from DMSO, but I'm also not sure what's actually driving the pH and how are different acids interacting with PFAS and the particle. But it would be very interesting to look at this.
Questions?
I have one basic question. Why PFS is important?
Yeah. The first reason is that they are persistent. So they stay in the environment. And second, they have a lot of health-related issues. So I told that they could cause reproductive teeth damages. More than
Concentration is safe.
any concentration.
Any concentration.
Yes, any concentration is harmful.
It's because of increasing anthropogenic activity, or you can see fresh water also, fresh ocean water.
So PFAS is anthropogenic. So what we did not sample any freshwater samples. Like it's basically all anthropogenic that was dumped into the oceans, and then it's coming back to haunt us in the form of particles and gases from sea spray aerosol.
So that is only the reason. It's
I'm not sure. They haven't, at least I haven't come across a study, but I think because they are so surface active, they might also act as CCMs, but that's something to be tested. I'm not
Very small source. Yeah.
Mm.
But yeah, it's a global
as
pollutant.
of now, it is basically a toxicity.
It's like mercury. Even
What is the flux of PFAS in ocean? Like how much concentration? Like you go much closer. Water.
PFA is 200 nanograms per liter. That's the average.
Surface water. Surface or
I think it's the global ocean concentration.
so generally it high in at the surface and low at the bottom.
I don't know gas phase.
yeah, please, Shubha.
Okay, just one like suggestion whether it is doable or not. So like what you showed one like a closed chamber experiment, so where you are like passing that same like chamber based PFA emitted like aerosol stream or gas stream into a bottle of sulfuric acid. You're sampling it in CIMS, right?
No, I think I miscommunicated then. We just transferred the whatever we had in tank into the bottle. So we added real seawater in the bottle.
Yes.
And then excited.
Whatever emissions were there, they were into the bottle of.
When we used the bottle, it was only
Instead of the tank.
Okay, no time.
I only added drops of sulfuric acid on the top.
You didn't do any studies with other acids. So, for example, increasing your organic acids in the.
Try to correlate with different total signal of organics and multi. We find some positive correlation, but I was not so sure about it.
And you also haven't done any experiments of exposing your aerosols to acids in the atmosphere. Right. That might be very interesting to do because that would be a lot more realistic, saying that instead of changing the acidity of the water, you change the acidity of the air that you are exposing the aerosols to.
Actually said that, but actually I was going to suggest. So only that, not only the acidic one, you can send it to the like base one also, like ammonia mediated environment. Then you can sample like there will be like two-way sampling, one with the acid one with the acid, then ammonia, then the CIMs. That will like strengthen your hypothesis in more way.
And we would have loved to do that, but there were some time constraints. I could manage ambient and lab experiments, but it would be interesting to somehow verify what drives the pH of sea spray aerosol particles. If you have any ideas, what could be changing the pH? Because average water pH is about 8, and the aerosol pH is 2. I'm perplexed. What is driving the change? Is it only drying up, concentrating the acids, or do you have some more ideas?
Drying up and aging. Aging leads to a lot of exchange. And there are plenty of studies showing why this acidity increases significantly. And especially in coastal regions where you have your sea salt coming in contact with continental air masses.
that particular thing, but well, that's just my basic idea or just a curious question, you would say.
This is not atmospheric. This is seawater.
Seawater.
Coming gas phase drops.
Gas phase PFAS.
It's in your tank, right?
Yes.
With seawater.
Oh, so the sample is from the seawater.
Yes.
Okay, maybe that is the one. Maybe okay.
Yes. It's going to say the other reasons could likely be the
Please.
difference in salinity.
Okay.
Because the global ocean is 30. It's just 5 and 1.
So, and this sample was collected only once, or is it a periodical collection of the sample? Okay, within a span of 45 days. Okay. Okay.
Times. And I tested a lot of conditions. I also tried to certain steps and get a plot of pH versus PFAS emissions, but that did not work because every time I add like a bit of acid, it buffers and neutralizes. So I have to go straight to 2 or
You did not filter the seawater. That's one way to reduce the buffering is remove all the organics. Organics, I mean, your carbon.
it simulate increasing CO2.
No, if you just filter off all the organics like particulate organics, etc., then you can change acidity.
Okay. Any more questions? If not, let's thank Sneha again for the wonderful talk. Thank you, Sneha.